Hello. Welcome to our first video back for semester 2, eh? Welcome, welcome. This is our first occasion where we will have questions within the video. So make sure to answer those. You will be prompted as you watch the video to answer the questions. And if for some reason you aren't prompted, then you probably clicked the wrong link or you just need to refresh or something like that. But it ought to work for everybody. So just putting that out there. It's our first time doing that. So we're doing 6.1 geometry, 6.1 notes. We're talking similarity. So what does it mean for something to be similar? Let's take a look here. Two polygons are similar if and only if one can be obtained from the other by a similarity transformation. Okay, what are similarity transformations? Let's look at the bullet right above it. A similarity transformation is a transformation in which the image has the same shape as the preimage. Specifically, similarity transformations are the ones that we know: reflections, translations, rotations, and dilations. When you do any of those transformations, you end up with something similar. We talked about rigid motions, meaning that something's congruent. It doesn't matter what I do to this remote, whether I rotate it, slide it around, or flip it over, it's still the same remote. The same is true here, but when we dilate, it makes the remote bigger, right, or smaller, and then it's no longer congruent, but we say that it's still similar. The important thing is that similar figures are the same shape, right? That's also kind of what this is saying. All right. So it doesn't matter whether you move it around, make it bigger, make it smaller. You can tell that this triangle is essentially a smaller version of this triangle, right? They look exactly the same. And this triangle is the same as this triangle. It only got slid around. But in the end, all three here are similar to one another. Okay? All three are similar. Similar just meaning the same shape. So, a valid similarity statement must match corresponding angles and sides. So what is a valid statement for the triangles above? Okay, so we were writing things like, oh, triangle ABC is congruent to triangle XYZ, right? We've written stuff like that before. Okay, we're not going to write that exactly. We're going to write a similarity statement. A similarity statement uses a little squiggle to represent that they're similar. Okay, so I'm going to say that this triangle and this triangle are similar. How do we write that? Well, triangle ABC is similar to, and let's make this the first question. Here's the first question, folks. What point matches up with A over here, right? Obviously, this triangle is the same as this one. A matches up with what letter? D, E, or F? Answer it. All right, I should have popped up on the screen for you. You answered. You should have said D, right? That point matches with this one. Yeah, it does. And B matches with E, and C matches with F. You see how those are matching up? Okay, so one of the big things that we'll see is that when we dilate figures, make it smaller or bigger, they're still similar. And dilation always used a scale factor. Let's remind ourselves, how do we find a scale factor? A scale factor is image over pre-image. And you're going to be asked several questions on the classwork, just some review. Hey, find the scale factor of this. Find the scale factor of this, right? So let's do that. What's the scale factor here to go from ABCD to EFGH? Well, ABCD is the big figure here. That's 1, 2, 3, 4, 5, 6, 7, 8 long on that side. And EFGH, that's the small square here. That's only 2 wide. Image is the after. So if we're going from this to this, this is the pre-image, and this is the image. So image over pre-image, meaning 2 over 8. So the scale factor is 1/4. It got 1/4 smaller. It shrank down by 1/4. What is the scale factor the other way around? Well, now this has become the image, and this is the pre-image. So 8 over 2, the scale factor is 4. We're multiplying by 4 in order to make it bigger, right? And we're multiplying by 1/4 in order to make it smaller. It all depends on the direction that you're going. And that arrow is telling us the direction. We are shrinking, we are enlarging. Okay, so again, determine if figures are similar. What makes them similar? If they're the same shape. Are these two triangles the same shape? Yeah. It looks like to me it got dilated and blown up, right? It got stretched out. So are they the exact same shape? No, they're not congruent. But are they overall, do they have the same proportions? Yes. And I'm going to say, what's my reason why? RTS can be dilated to form triangle X, Z, Y, right? We can take that small triangle on the inside and blow it up, and all of a sudden we'd have the big one. What about here? Are these the same? I hope you're saying no, right? This is a completely different looking triangle, right? This isn't a rotation or a dilation or any of those things, right? It's just a completely different triangle. So in this situation, we would say no. They are not the same triangle. Nope. No sirree bobber. All right, moving on. Similar just means, hey, they look the same. They look similar, right? I mean, similar is such a perfect word, right? I think we all know what similar means. It's the perfect word to describe the situation. So here's a little pro tip. If all of the angles of two triangles are equal, well, then those two triangles are similar. Right? If all three angles inside of the triangle are the same, they're similar. And that was the big giveaway on this one as to why they weren't similar, right? This angle is significantly different than this one, right? This might look the same as that, right? But this angle is not the same as that one, and this angle is not the same as that one. They are not similar. You're really contorting the shape and changing what it looks like. So if the angles are all equal, then you know you have similar figures. So like, look here, look at this. These look like, they both have a right angle, and then this angle that's being created with this dotted line looks the exact same to me, right? And so does this, right? These figures are similar. In order to find the height of a palm tree, you measure the tree's shadow, and at the same time of day, you measure the shadow cast by a meter stick that you hold at perpendicular to the ground. The measurements are shown. So let's really stress the fact, hey, we got this right angle, okay? You can assume the rays of sun are parallel, okay? Here's the sun, and we've created these sun rays that are coming down are parallel, all right? The dotted lines are parallel. And why is that important? When we have parallel lines and they're colliding with the ground, we just created some alternate interior angles, corresponding angles, stuff like that. You remember those buzzwords? Okay? So this angle right here and this angle right here are corresponding. Okay? They are corresponding, right? I can literally take this angle and drag it over, so to speak, and it would just match up, right? They correspond. So this angle is the same as that one. And that's actually what the first question asks. I kind of forgot that. The first question asks, what can you say about angle C and angle Z? Well, they're equal. Why? Because they are corresponding. So how is ABC similar to XYZ? Well, if this is 90, right? If that's 90, I'm not going to bother writing. If that's 90, and this is 90, and let's say this angle's 40, just for grins, well, then this angle has to be 50, right? All three angles are the same. If these two are the same, well, then the third one has to be the same, right? Because they both will add up to 180 in the end. So I'm going to use that little tip over here, right? How are they similar? Because all angles are equal. So let's solve for the height of the tree. How do we do that? Well, it all comes down to what we were sort of practicing here, scale factor. And a lot of the classwork will be solving, of course, right? So here we are getting to the nitty gritty here. How do we solve? How do we use scale factor? Well, this thing is getting bigger, right? We started small and we're getting bigger. Scale factor is image over preimage. Image over preimage. So if we started small, that's the preimage, and we ended up big, that's the image. Well, let's do image over preimage. 7.2 over 1.6. And when you plug that into a calculator, you get 4.5. So the scale factor is 4.5. What do we do with it? Well, everything is 4.5 times as big. Not 2 times as big or 3 times as big. It's 4.5 times as big. So what's the height of the tree? Well, you take the meter stick and multiply it by 4.5. Oh, well, 1 times 4.5 is simply 4.5. The height of the tree is 4.5 meters tall, which is what? Like 13, 14 feet. So, I mean, that's decent sized tree. So you find the scale factor, use the scale factor. We're going to do this like 3 more times here, okay? So get in a rhythm with me. I'm going to do one more and then let's do another question here, another question prompt. So let's do another one together here. A 6-foot tall man casts a shadow that is 7 feet long. At the same time, the shadow of a tree is 28 feet. How tall is the tree? So a very similar question, right? Don't get yourself too confused. We have a 6-foot tall man casting a 7-foot long shadow, and then we have a tree that we don't know how tall it is, but we know it's got a shadow of 28 feet. So we've got this same situation. Here's the sun. We're casting a shadow. There's the sun rays. Right? So we've got the exact same situation as above, right? And again, we are getting bigger, right? We have a short man, relatively speaking, compared to the tree. And so the shadow over here is smaller, and everything's enlarging. By how much? You probably can just eyeball it. If the shadow for one is 7 feet, and the shadow for the tree is 28 feet, you can just probably eyeball it, right? It's times 4, right? It's 4 times as big. But again, how do we do that? If you need a formula, right? Well, we started out with the 7. We ended up with a 28. Image over pre-image. We end up with 4. 28 divided by 7 is 4. So if we have a 6-foot tall man and we multiply that by 4, we end up with a 24-foot tall tree. 6 times 4. Okay, so Mr. Skis, I need to get from point A to point B. I'm about to ask you a question here. How far will he have to travel? So this triangle is similar to this triangle. Okay? So I'm not trying to make these questions hard. I just want to know that you're paying attention. So this side right here matches up with this side. What's the scale factor to go from 7 to 14. We're obviously enlarging. The scale factor is... Question pops up on screen. The scale factor was what? You should have answered 2. I'm using K for scale factor. The scale factor is 2. The triangle on the left is twice as big. So if this distance right here, it might be kind of difficult for you to realize that what I intended to label was this right there. That's 5 miles, okay? Well, then how long is AB? Hopefully you realize that this is a rotation, by the way. Let me help you out visualizing that. If I draw this purple triangle and then I rotate it, give me a second here. If I rotate it, you can see, oops, sorry. Come on. No. Rotate, you sucker. It hates me, guys. There we go. Look at that. So if I rotate, you can see how it's matching up, right? So how do I do that? This side is wrapping around and matching up with this one. That's what I want you to see. And this back side wrapped around and matched up with this one, right? It's a rotation. So if it's getting twice as big, and right here it was 5, well then as it wraps around, from A to B is 10. You with me on that? I hope so. So each of these problems, find the scale factor, use the scale factor. Find the scale factor. What is it here? We got a big ladder and a small ladder. All right. The big ladder is 55 feet tall. The small ladder is 22 feet tall. What are we trying to find? How far up the wall does the short ladder go? I'm going to use H for height. So in this situation, I'm trying to shrink the big ladder to take a guess at what's happening for the small ladder. So this has sort of become the pre-image, and this is the image. We're not trying to get bigger here. We're trying to get smaller. So again, image over pre-image is your scale factor. So I've labeled them quite clearly here, which one's which. Pre-image is the big one, because I already know all there is to know about the big triangle. We know how long the ladder is, and we know how high up the wall is. So I'm trying to solve for the image here. So 22 over 55, the scale factor is 2/5. Anything less than 1 always shrinks, right? So we did it right. 2/5 is less than 1. So we use the scale factor. We found the scale factor. Now we use the scale factor to solve for the missing side. So this missing side that we're trying to find corresponds with the 35. So we take the 35 and multiply it by 2/5, right? It's no different than what we've done in the previous problems. I understand we're multiplying by a fraction, but it's still multiplication, okay? Times 2, times 4, a little bit easier, I know, but we're shrinking this time. So we're multiplying by this fraction, 2/5. 35 times 2 is 70. And then 70 divided by 5 is 16. 14, sorry, 14. 14 feet. Find the scale factor, use the scale factor. Okay, last two problems. What are we at? 19 minutes? Okay, I'll try to go quick, but not too quick. I just don't want the video to be too long for you. So if EF is parallel to BC, then voila, you've created two similar triangles. It's a similar triangle inside of a similar triangle. Kind of cool, right? All because these two sides are parallel. Well, here's a nice little relationship that occurs. AE over EB is equal to AF over FC. Let me highlight that, right? AE over EB and AF over FC. You see how there's two halves? There's this half. Let me use a different color. There's this half and there's this half. There's this half and there's this half. So we're saying the top half over the bottom half. Now, they're not actually always equal. As you would see here, they're not actually equal. Okay? But this is the top half, this is the bottom half. This is the top half, this is the bottom half. So we're going to have to use that in just a second. Tell me, which one's the easiest to find? Which one's the easiest to find? Think about that for a quick second. It's x, right? Because I know that this is 20, this is 5, so x has to be 15. 15 plus 5 is 20. Okay, so boom. I can set up that proportion over here. Top half is 15. When I say top, it's relative, right? There's two halves. There's this half and there's this half. There's this half and there's this half. So the two ends that are close to the vertex here and the two that are further away, right? So 15 over 5 equals y over 4. 15 over 5 is 3. So 3 equals y over 4. You remember how to do stuff like this when we set up a proportion like this? We cross multiply. 4 times 3 is 12. 1 times y is y. So y is 12. Remember you've seen cross multiplying. And then z is super easy if we know that y is 12. 12 plus 4 is 16. So I hope you see how these matched up here, right? I know the letters are different than the letters on here, but don't think about the letters. Think about what you're looking at. Again, I can't stress enough that there's like E is splitting up this side. R is splitting up this side. There's this half and this half. So I'm matching up these two halves, 15 and y, and 5 and 4. You see that? So I can do the same thing here. I can find x first, just like I did in this one. So if the whole thing's 56 and this is 40, boom, I know that x is 16. Okay, so I'm going to fill in nearly all of it, and this is the last question that I want you to answer. So I had you... so this is x is 16 over 40. And then this is going to be what over what? What should it be? I'm probably going to do multiple choice right now. Okay, so you saw some options. What did you end up choosing? It should probably be what matches up with x, 20, and what matches up with the 40, the z. You see that? So these are both divisible by 4. Actually, they're both divisible by 8. So we end up with 2/5 equals 20 over z. And then cross multiply. 2z equals 100. 5 times 20 is 100. Divide by 2. Z equals 50. So z is 50. Y is super easy to get then. 20 and 50 make 70. And then W. All right, what are we at? We're at 23 minutes. Okay, it's probably going to go to 25. So look at this blurb that I wrote here. Other relationships we've been using are still true when it comes to these triangles. You've got the small triangle and you've got the big triangle, right? They're similar. We got A, E, and F, A, B, and C, right? Referring to this triangle up here. I've just separated them. We still have the luxury of scale factors, right? We still have the luxury of scale factors. Let's call this the image and this the pre-image, right? Image AE over pre-image AB. We've got image AF over pre-image AC. We've got image EF over pre-image BC. All three of those are equal because scale factor is consistent. Scale factor is consistent. It doesn't matter which two sides you take. You're always going to get the same answer. Let's say that this triangle is 3 times as big. It doesn't matter whether you do the left over the left or the right over the right. You're always going to get 3 because the triangles are 3 times as big. So that's why all 3 of these are equal to one another, because scale factor is the same no matter how you look at it. So why do I bring that up? Because the last question here, we want to enlarge 12, we want to dilate it, we want to use our scale factor to determine W, right? We got the small triangle and the big one. So what's the scale factor here? Well, image over pre-image, we want to take the small one, that's our pre-image this time, and create the big one, that's our image. So image, how long is this side right here? Or this one, right? You could use the y value that we found, or you can find the one that's given to us, the 56. It doesn't really matter. And I can show you both if you're interested. So this is 56, and x right here is 16. So 56 over 16 equals, what is that? 3.5. So if I take 12 and multiply it by 3.5, what do I get? 42. So W is 42. But wait a minute, let's do the other one just for fun. What if you decided to use 70 and 20? Well, image, 70, over pre-image, 20, the big over the small. 70 divided by 20, guess what? I get 3.5. I get the same thing. It doesn't matter which way you look at it. And again, 12 times 3.5 gives you 42. All right, thanks so much. Thanks for answering those questions. Not going to keep you any longer. I'll see you in class.